Hey everybody, Ripley here. Welcome back. We're going to talk a little bit about probability distribution and random variables in this chapter. This is chapter 5. And we are cruising right along. Hopefully you're starting to get into the swing of things with this classroom flipping model and aren't getting too frustrated. Remember, talk to me if you're having problems. We can figure some stuff out. All right? Let's go and talk about a random variable first. All right? A random variable is simply random variable. It's a variable with numerical value. So we're talking about numbers here. All right, numerical value whose outcome is determined by chance. Is determined, or you'll hear this sometimes referred to as probabilistically. Okay, determined by chance or a certain probability. All right. Now there are two types of random variables. There are discrete random variables. So there's discrete RVs, which just like we talked about before with discrete numbers, their outcomes are going to be 0, 1, 2, 3, etc. All right, basically the whole numbers. Think of it as what you would roll on with 2 die. We're gonna actually build something by rolling 2 die here in just a sec. Excuse me. That's a discrete random variable because I roll a 2, I roll a 3, I roll an 11, I roll an 8, etc., etc. I can't roll 7.3. Now that's going to feel a little strange when we start talking about something called expected value and means, but you'll see what I'm talking about when we get to it. And then of course there are continuous RVs. All right, and these are on a continuum. All right. An example of this would be like amount of gas I have in my car. Not in my belly, in my car. I can have, well, God, I hope not, 17.9352214 gallons of gas in my car. I could have 2 pi gallons of gas in my car. In other words, it can be any number from some starting point, which in this case, excuse me, because we're talking about a ratio measurement. Remember, ratio measurement it's the highest, it's the most precise of all of the variable measurements. Okay. Remember, nominal, ordinal, interval, ratio. It would start at 0, and theoretically, if you had a really, really big car, it could go to infinity. All right. Now, what we're going to build from these is called a probability distribution. Probability. So we take these random variables and we organize them into a probability distribution. And very much like our frequency distribution, remember we've heard of distributions before, what we get is sort of a graphical account of what's going on. All right. Now, I'm going to build a probability distribution, but before we do that, I'm going to I need to set the requirements for a probability distribution to be a probability distribution. And the first of these is that the sum of all of the probabilities in the distributions have to add to 1. They have to. In other words, something's got to happen. If I roll 2 die, there is a probability that's associated with every single number that I can possibly get. All right, and the sum of all of those probabilities has to be 1 because something happens when I roll die. All right. Second is these probabilities, just like all probabilities, this is sort of a superfluous one, have to be between 0 and 1. Okay, so let's do this for 2 die. So we're going to roll 2 dice. 2 dice. All right, now let's think of the outcomes here for just a sec. All right. The possible rolls that I can get on 2 dice are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. All right, these are called snake eyes, those are boxcars, etc., etc. In craps, that's a really important number because after the first roll, if a 7 pops up, everybody's money gets scraped off the table. Okay, so let's think for just a sec. What is the probability of rolling a 2 with 2 die? Well, the first thing we better think about is the sample size. How big is the sample size, or what is the sample space for rolling 2 die? Well, it's going to be 6 on the first die times 6 on the second die. Okay. Now, sometimes students are like, wait a sec, Ripley, why isn't it just 12? Well, the fundamental principle of counting, since I'm rolling 2 die to make a roll, the fundamental principle of counting tells me that I have to multiply those. But an easier way to think about it is I can get a 1, 2, 3, 4, 5, 6 on the first die, a 1, 2, 3, 4, 5, 6 on the second die, and then you just match these guys up pairwise. So I can make a 1, 1, a 1, 4, a 1, 5, a 1, 6, a 2, 1. Let me change colors with this thing real quick so I can show you this, because this is kind of important. I can make a 2, 1, whoop, like that. This is where students will often say, wait, Ripley, why is the 1, 2 different from the 2 and the 1? Because they're done with different die. If you colored your die, let's say that these guys were red and these guys were green, get out of there, and these guys were green, then clearly a 1 on the red and a 2 on the green is different from a 2 on the red and a 1 on the green. So there are 36 different ways to roll. There are 36 different outcomes when I roll 2 die. Okay? Now, how can you roll a 2? Well, there's only one way to roll. It's called snake eyes, and that's a 1 on the first. Get out of there. There's a 1 on the first and a 1 on the second. So we got 1 out of 36. All right? Now, let's figure out the probability of rolling a 7 with 2 die. All right? All right, so let's think about this. There's a 1 and a 6 and a 1, that's 2, 2 and a 5, 5 and a 2, that's 4, 3 and a 4, 4 and a 3, that's 6. There are 6 out of 36 ways, excuse me, to roll this, or 1/6. So approximately 1/6 of the time you're going to roll a 7. Approximately 1 out of 36 times. 1 in 36 times, you're going to roll a 2. Now, be careful. Remember, law of large numbers says that you have to do that a whole bunch of times to have that thing head for the value for the theoretical probability. Okay? All right, now, a probability distribution is kind of like a frequency distribution that you just flip on its head. It's easy to make. So all we do, we're going to put our x values here. Our x's are the numeric outcomes, okay? So, oh wow, that's just horrific. Let's try that again. Sorry, again, hard to do this at your belly button when you're not looking at it. Come on now, don't be shy. Okay, there we go. And we're going to get a 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And we'll pretty this up just a little bit, just so it doesn't look so terrible. All right. Now, here we go. We just figured out that the probability of rolling a 2 is 1 in 36. Now, if the probability of rolling a 2 is 1 in 36, isn't that exactly the same thing as the probability of rolling a 12? Because that's a 6 on the first and a 6 on the second. If I flip those around, I still get the same roll. So there's 1 in 36 ways to do that. All right, so let's think about a 3. I can roll a 3 by rolling a 1 and a 2, or a 2 and a 1. No other ways. It's not like I can roll a 3 and a 0 or a 4 and a negative 1. That just don't make no sense. So there are 2 out of 36 ways to do that as well. Think about an 11. Wouldn't that be exactly the same thing? 6 and a 5, 5 and a 6. So I get 2 out of 36. And then 4. Now let's think about a 4. I can get a 1 and a 3 and a 1, and a pair of 2s. There's a name for that, but I forget what it is. So 3 out of 36. 10, same thing, right? 6 and a 4, 4 and a 6, and a pair of 5s. So that's going to be 3 out of 36. You're probably starting to see the pattern, but let's go ahead and go through it. How about a 5? 1 and a 4, 4 and a 1, 2 and a 3, 3 and a 2. That's going to be 4 out of 36, which it makes sense that that's the same thing with a 9. 6, 3, 3, 6, 4, 5, 5, 4. And I end up with 4 out of 36 over here. We already did 7, but we'll get there in just a sec. 6 is 5 out of 36. Let's do 6 real quick. 1, 5, 5, 1, 4, 2, 2, 4, and a pair of 3s. So this is also, thinking about it, with 8 is going to be 5 out of 36, and then 7 out of 36. Now, if I add these up, think about that. Whoa, 7 out of 36. Where'd that come from? Ding dong. This is 6 out of 36. All right? Now, I can add these up. Let's make sure that, remember, according to our rules of a probability distribution, all of the probabilities have to sum to 1. So 3, 6, 10, 21, 30, and 36. So the sum of P of X is equal to 1. Whew, thank God. Now, what do you think that the average roll would be? All right? In other words, on average, what would the roll be? Now, if you remember from way back in the day when we found the mean, remember when we found the mean of frequency distributions? Remember what that was? The mean of a frequency distribution, assuming it's a population, and that's completely, if you think about it, we're going to be talking about this as though it's a population because it's really the set of all outcomes that are possible. It's not like I took a sampling of outcomes that are possible when rolling 2 dice. All right? So remember from the frequency distribution, what did we do? We took what was it? It was F times, remember, X with the midpoint, and then we divided by N. All right? Well, watch how cool this is. I can actually build out the frequency, or excuse me, the mean of a probability distribution from this definition. Check this out. It's so easily done. If I put F divided by N, isn't that the definition of probability? So I don't have any sort of midpoints because I'm not talking about class values. I'm not getting a roll between 1.5 and 2.5. I can only get a 2. I can only get a 3. It's not as though the die is going to balance on an edge or on a point. So I could rewrite this as the sum of X times F divided by N. Well, or excuse me, that should be a capital N. F divided by N, capital N, F divided by N is the probability. So I end up with X times P of X. Whoa, that's pretty cool. So the mean value, the mean roll that you would get when rolling 2 die is going to be the sum of this times this, plus this times this, plus this times this, etc., etc. Not only is that true for this probability distribution, but it's true for all probability distributions. You might want to memorize this guy. Okay? Now, I'm going to let you guys use some notes on exams and things of that nature, and we'll negotiate, excuse me, for what you're gonna be able to use. However, I do want you to be able to have these at your fingertips. So again, just fire yourself off a little note card. You know, it's like memorizing vocab, like anything like that. Hey, let's figure out what the average roll is real quick. So the mean of this guy is going to be, well, all I'm going to do is add up this times this. So 236 plus 636, that's 3 times 236, plus 1236 plus 2036 plus 3036 plus 4236, and then I can go down again, can't I? Oh, I can actually, because the value is different. I get what, 4036 plus 36. I do go down, but I don't. It's not symmetric. 3636 plus 3036 plus 22, 36 plus 12, 36. If I throw that in my calculator, if I do it by hand, I get 252, sorry about the margin, 36. That looks a little funky. If I throw it in my calculator, guess what I get? 7. The average roll, excuse me, the average roll with 2 die is a 7. It's the one that occurs the most. It is at the center of the distribution, literally as well as mathematically. Okay? I wonder why the casino makes it so that you quote-unquote crap out, or it gets to collect all the money when a dice player rolls a 7. Now, I'm going to show you another one that let's just roll 1 die, and we're going to do exactly the same thing. So instead of rolling 2 dice, let's roll 1 die. All right? Well, we got X, and we got P of X. And this one's a little easier, right? Because I can only roll, that's pretty good, 1, 2, 3, 4, 5, and 6. So if I throw these guys in, this one gets super simple. We know that the probability of all of these is 1/6. 1/6. They're all 1/6. Whoops. So if I want to find the mean for rolling 1 die, what is the average value when I roll 1 die? Well, look at it. It's 1 plus 2 plus 3 plus 4 plus 5 plus 6, all over 6. 1 times a 6 plus 2 times a 6. I just found the common denominator, right? Let's see, that's easy, right? That's half 3, 21 sixths, 21 sixths, which is 7 halves or 3.5. Now sometimes I get students and they're like, wait a sec, how can you have a roll? How can you have an average that isn't even rollable? In other words, it's impossible to roll a 3.5, right, with one die. It's not like if it lands on its edge and it sticks there, if it falls in a pile of sand and it sticks on its edge, that you've rolled a 3.5. You've either rolled a 3 or a 4. But think about that. We're not afraid of that. Averages work out that way all the time. If you think about the average number of kids that the traditional American family has, is like 2.7 kids. You can't have 7/10 of a kid. It represents an average. Over the course of many rolls with one die at a time, if I add up all those values and I divide by the number of rolls, I will come up with, after many rolls, a number very close to, if not exactly equal to, 3.5. So we're not afraid of that sort of a number. It doesn't have to be, even if our random variable is discrete, there's absolutely no reason that our mean is going to be a discrete value either. In fact, it very rarely works out that way. It's special in the 2 dice case, but like I said, it very rarely works out that way. Now, I'm going to give you the variance of these guys real quick. And again, don't freak out when you see this formula. I'm going to give you one that, let me just write them down for you. All right, so I'm going to take x minus mu, and you can actually see why this happens times p of x. All right? And then this is actually the formula. Now, remember back here when we came up with the mean? We got this mean from a frequency distribution. Now, we haven't gone into it much in this class in terms of trying to figure out how to find a variance in a frequency distribution, and we won't. But you can kind of see where this works out. Remember, probability is f divided by n. We've seen this before with variance. We're not afraid of this x minus mu thing. All right? So this is a real good way to understand how to find the variance of this guy. Remember, variance is what? Think about that. It's a measure of spread, it's a measure of variation, and it's also the standard deviation squared. However, and again, this is an introductory statistics class, so we're not going to go hugely into where these formulas are derived from. So you're going to have to take it a little bit with a grain of salt. There's an easier way to do this computation. Check it out. If it's the sum of x squared times p of x. To be honest with you guys, I don't remember these formulas if I can avoid it. And then all that I do is I just look them up when I need them. All right, because a calculator can spit them out. There's lots of ways to do this. This is an easy way to understand it theoretically. This is the easiest way to do it computationally. Okay, excuse me. I'm going to do the variance for the die, for a one die roll. We'll do that right now, just so I can show you. Okay. Now, what I'm going to do is I'm going to add, notice with this formula, I need the sum of x squared times p of x. So what I'm going to do is I'm going to add an x squared right here. Let's stick x squared right in here. So we're going to drop this down. I'm going to get a 1, a 4, a 9, a 16, a 25, and a 36. All right? Now, let's do this just a little bit at a time. We'll take our time. So this is going to be the sum of all of these x squared times their appropriate probabilities of that. So x squared times p of x. So that guy right there. So I'm going to get 1/6 plus 4/6. I'm going to not reduce it just because it's easier to do the mathematics. What is this? Plus 9/6 plus 16/6 plus 25/6 plus 36/6, right? That's this right here. And then I'm simply going to subtract out 3.5 squared, or 7/2 squared, by the time I'm done. All right, now let's see if we can do this thing in our head. There's 10, there's 20 for 30, 55, 85, 91. So I got 91/6 minus 49/4. That sound right? So what? 182 minus, oh God, 150, 147, 147 twelfths if I find a common denominator. Double check that to make sure I didn't do anything stupid. Let's see, 3, 120, yeah, 147. So what do I have here? 35, this is 35 twelfths, right? 35, yeah, looks good to me. Now, this is the variance, but remember, the standard deviation, sigma, is going to be the square root of the sum of x squared times p of x, right here, whoops, minus mu squared, that's this guy, which in our case is going to be the square root of 35 twelfths. Now, think about this. What's the standard deviation going to be? It's probably going to be relatively small because all of our values are between 1 and 6. They're uniformly grouped between 1 and 6. So let me throw this in my handy-dandy calculator because I'm good, but I'm not that good. Let's see, 35 divided by 12, and I'm going to get, let's see, booyakasha, I get approximately 1.71. Well, there you have it. That is the standard deviation of a one die roll. We will get an average of 3.5 on every roll, excuse me, with a standard deviation of 1.71. Now, let me show you something. This is kind of cool. Remember our rule about unusual, quote unquote, unusual rolls or unusual outcomes. And remember, once we had standard deviation, outcomes, we had a great way of sort of defining that. If I take the mean, which is 3.5, and I add 2 times the standard deviation, I get 1.71, right? So this is going to be 3.5 plus what? 3.42 approximately. No, exactly. And I'm going to get a 6.92. So if I get a value when I roll a die that is greater than 6.92, I get an unusual roll. Well, I'm only rolling one die, right? It's going to be, I can't roll a 6.9. I can't roll a number bigger than 6. Same thing, if I go 3.5 minus 2 times 1.71, right? Then this is 3.5 minus 3.42, and this is 0.08. If I get a roll that's less than 0.08, it's unusual. Now, think about this. These probabilities are uniformly distributed. In other words, everybody's got the same probability. So there better not be such thing as an unusual roll or all hell is broken loose. Unlike over here, there may or may not be. Maybe a 12 or a 2 is an unusual roll. We could go through the process if we wanted to. It takes a long time, though, unfortunately. Excuse me. We can go through the process of figuring out what the standard deviation is of this guy, but I'm not going to subject you to that sort of pain. All right? Those rolls, the 2 or the 12 with the 2-die roll, may be considered quote-unquote unusual, but when I've got every outcome having the same probability, I better not get any unusual rolls, or something has gone horribly wrong. All right? Well, that gets you where you need to be as far as the brick and mortar. Remember, mean, standard deviation. Those are our buddies when we're talking about probability and statistics. That's where everything starts. Hopefully this was helpful. We're going to talk about expected value here in just a second. Okay, the last thing that we're going to talk about out of this section is something called expected value. Expected value is the most important thing when you're talking about any sort of gaming or gambling system, because I'll show you why here in just a sec. Because it's going to dictate how much money you're going to win or lose if you're the house, or if you're a gambler, it's going to dictate how much money you can expect to win or lose per play of a certain game over the course of many plays. All right, so let me try to explain this to you. Let's make up the simplest craps game ever. I'm going to hand you, excuse me, I'm going to hand you some dice, and I'm going to say, roll the dice, and if you get a 7, I'm going to, let's assume that you bet, I don't know, what's a reasonable bet? $1, okay? If you win, I'm going to hand you your dollar back, and I'm going to take, I'm going to try that again. I'm going to hand you your dollar back, and I'm going to give you, let's go $4, okay? And if you roll anything other than a 7, I get to take your dollar, all right? So watch this. I'm going to create a probability distribution to model this. Now, think about it this way. I don't have to build that probability distribution that I did before. I don't have to build this guy because my outcomes are going to be based on money. All right? I don't worry. Remember, you either roll a 7 and get paid, or you roll a not 7 and don't get paid. All right? Again, I'm overly simplifying a craps game, but we won't, no panicking. All right, watch, check it out. So what did I say? I give you, if you roll a 7, and we know that the probability of rolling a 7 is 1 out of 6. If you roll a 7, I give you your dollar back plus what I say, $4. So you are up $4. You're not up 5 because you had that dollar in your pocket to begin with. Otherwise, you lose $1. All right, so this has to be 5, 6. Now, the expected value of the game, this is sometimes written as E of X, is actually the average value of the game, which is the sum of X times P of X. So in this case, all I have to do is multiply this times this, and this times this, and I add it. Now watch what happens. 4 times a sixth plus -1 times 5/6, and I end up with -1/6, right? Which is approximately equal to, what, -17 cents, more or less. It's about what a sixth is, 17 cents. All right? Now, this is where students start getting glassy-eyed and go, what? Again, this doesn't make sense. I didn't make that bet. I can either win 4 or I can lose 1, and you're talking about 17 cents. Okay. Here's the way this works. If you play this game over and over and over again, sometimes you're going to win $4. Sometimes you're going to win, or you're going to lose $1. However, if you take the average of all of those outcomes, all right, if you take the average of all of those values, you can expect to lose 17 cents on average every time you play. Now, again, I realize that doesn't qualify as one of the outcomes, but remember, we're talking about an average here. Okay? So think about it. If you're the casino, this is a great game for me. Even though sometimes I'm going to lose big bucks, well, $4, sometimes I'm going to lose big bucks, well, that doesn't frighten me at all, because on average, as long as I can keep you playing, and that's key, as long as I let the law of large numbers come into effect, let's write that out, law of large numbers. As long as I let the law of large numbers do its thing, I am golden, because I can expect to make 17 cents on you on average every time you play. All right, I know I said on average about 19 times, but that's really, really important. But the key is keeping them playing. So think about Megabucks with their $250 million jackpot. Look, somebody's going to win this. But the expected value of the Megabucks slot machine, for all of those $250 million jackpots that they pay, there's a ton more people just pulling the handle, losing $5 at a time, $5 at a time, $5 at a time. Because the casino, the house, never gives you a game where the expected value is greater than 0. If they do, they lose money. And there have been some pretty notable cases where people were able to rig the system so that the expected value of a game popped up above 0. We'll talk a little bit more about those in class. Okay? So just a couple quick things. If the expected value of a game is greater than 0, this means that you gain money. Do the math. If the expected value of a game is less than 0, this means you lose money. Lose money. Whoops. Remember, we talked about this earlier in the class. If the expected value of a game equals 0, then you come out even. Nobody wins and nobody loses over the course of many, many plays. Okay? So you could actually tweak these payouts to make the expected value of this game equal 0, which is, it's actually relatively simple to do. Watch this. Let's say that I want X and I have P of X, okay? And I'm going to have 1/6. Again, this is just a really simple problem. I want to make this an even game. So here's what I'm going to do. I'm going to let's say that I bet $1 and I lose $1. And I don't know how much money to give, so I'm going to call this a variable. All right? I don't know what I want my payout to be. So I just simply call that some variable. Well, I know that the expected value of the game is equal to the sum of x times p of x. So I get m6 minus 5/6. If I want the game to be a fair game, then this is going to equal 0, right? So in a puff of algebra, guess what? M is going to be $5 if I solve for m. Think of it the other way. Maybe this is a little bit more, I don't know, nefarious, for lack of a better adjective. What if I want to make a little bit more money? What if I want to actually say, you know what, 17 cents a play just isn't making me enough money. So I need to figure out what to pay out. So instead of making 17 cents a play, I want to make 20 cents a play. We do exactly the same thing. I'm going to go x and p of x. This is how insurance companies do it. We've heard of actuaries. They figure it out, so on average, they make a certain amount of money off of each customer. Think of insurance as just being a great big gambling game. So I'm going to lose a buck 5/6 of the time, and I'm going to gain m amount 1/6 of the time. So it's the same problem. I know that e of x is going to be m6 minus 5/6. Only this time I want, now I'm thinking of this from the standpoint of the player because I'm losing $1 when I play. So the casino wants me to lose negative what? 0.2 or negative 1/5, right? All right. So in a puff of algebra, let's see how good I am. M6 equals, what is that? 25 minus 6, what is that? 19 30ths? That's not 19 30ths. What am I doing? So 25 minus 6 is 19. It is 19 30ths. Oh, times 6. So m equals 19 fifths. So now I'm paying out just slightly under $4, right? You see what that is? What would that be? That would be 380. So if I make m equal to 380, so 3/8, what are you doing? 380. So I give you your buck back plus 380. On average, I can count on making 20 cents per customer per play, as long as I keep them playing. Hey, I hope this was instructional. I love this stuff because clearly I'm a Nevada native. I'm a Reno native. Strangely enough, I was born about 2 blocks from where I'm teaching you right now. So it's in my blood, as it were. Thanks for paying attention. And we'll talk a little bit more about Chapter 5 in the next little lesson. All right, have a good